Hello, my name is Josh, and today we'll be talking about file I/O with Python. File I/O can seem daunting at first, but it is actually simple once you understand the model of how I/O works. We will build the model slowly, talking about each component one by one, and finally, we'll build a block diagram to help you see the big picture at the end of the module. Ready? Let's get started. A Python program that needs to work on existing data reads the data from a file on disk. After doing some processing, the Python program writes the data to a file on disk. The program reads the data from a file on disk into main memory and writes the data from the memory onto the disk. The Python program reads and writes to a file using an object called FILEHANDLE. In subsequent slides, we will discuss how to open, use, and close the FILEHANDLE. We will now explain various I/O scenarios. In this scenario, we open a file handle to a file in a temp directory. The first argument to the open function call is the path name of the file, and the second argument specifies the mode in which we want the file to be opened. There are many modes possible, though the most common modes are R for read and W for write. The open function returns a file handle that is used in subsequent function calls by the Python program. Next, we write a string to the file handle. On the following line, we again write a string to the file handle. Then we want to write an integer to the file handle, but Python only allows strings to be written to file handle. So we need to convert the integer to a string, and then we write the string to the file handle. Finally, we close the file handle so the operating system can free up resources, including memory associated with the file handle. Notice that after the Python program runs, we observe that a new 68-byte file was created. In a second scenario, we will read from the file that we just created. The Python program first calls the open function to open the file in read mode specified by the second argument R to the open function call. Next, the Python program calls the read function on the file handle, which reads data from the file into the memory buffer called file memory. The buffer file memory is an array, and we call the print function on it. Finally, we'll close the file handle to release operating system resources associated with it. In this scenario, we show how the memory buffer can be accessed like an array. So again, we open the file and get a file handle. Then we read from the file handle into the file memory buffer. Again, file memory is like an array, and we'll call the print function on it. We can call other supported functions like finding the length of the array and printing only the first 8 characters of the array. Finally, we close the file handle to release operating system resources. In this scenario, we'll demonstrate how to read line by line from the file. So first we open the file to get a file handle. Then we call the readLine function on the file handle to read one line at a time, and then we print the line. We repeat calling readLine and print the second line. Finally, we close the file handle to release OS resources. In this scenario, we show that once the file is read into the memory, the file handle is no longer needed and can be closed. So we open the file to get a file handle, read the file data from the file handle into the file memory buffer, and close the file handle. Now, when we print the file memory buffer, we can successfully do so, proving that the file memory buffer is independent of the file handle. But if we close the file handle, then we can no longer use the file handle to call other functions. We'll see this in the next slide. In this scenario, we will see that once the file handle is closed, it cannot be accessed. We open the file to get a file handle and perform readLine on the file handle. Next, we close the file handle. Now, when we perform readLine on the closed file handle, observe that we get an error because the file handle is closed, and the operating system has released any internal resources associated with the file handle. Here is an efficient way to read lines from a file. We open the file to get a file handle object. Then we call a for loop on the file handle object and print one line at a time. The end argument to print specifies that you want to print a new line after the print statement. The default of the end argument is \n, so we change it to null string since the input line already has a new line character at the end of each line. Finally, we close the file handle. This is a simple program to open the file and read line by line to increment a line count variable so that we can get the line count for the file. Similarly, we read the file contents into the memory buffer using the read function call and call the length function on the memory buffer. Surprisingly, we get the file byte count to be 0. Can you guess why? It's because the file I/O works like a music or video tape. The file I/O has a file pointer that is set to the start of the file when the file is first opened. As we read data from the file pointer is automatically incremented so that subsequent reads return the next data sequentially. In this program, we perform the reads on the file handle, and so the file pointer reached the end of the file. Now when we try to read from the file handle, it is already at the end of the file, so no new data is read. The way to fix this problem is to rewind the tape, or in this case, rewind the file by calling the seek function call, as we will see in the next slide. This program is exactly the same as in the previous slide, with the only difference being that we call the seek function call with an offset of 0 so that the file pointer is set to the start of the file. Now when we perform read on the file handle, we get the data starting from the start of the file, and hence the file byte count shows correctly as 68 bytes. Extending the previous example, if we perform a seek with an offset of 6 bytes, and then do a read of the file, then we get data starting at the 6th byte, as evident from the print of the memory buffer. As we come to the end of the file I/O module, let's see how we can handle errors gracefully. Here, we try to open a non-existent file and get an error that looks unreadable to the user. A good way to handle this error is shown on the next slide. Here we show how to use the try and except statements to catch errors, also known as exceptions. We try to open the file, and if there is an exception, then we print the appropriate message. Notice how the error is handled gracefully by the Python program instead of printing a non-friendly message. This type of programming is called the Pythonic way of doing good programming. Finally, here is the overall block diagram you can use as a reference for programming file I/O in Python. This completes the module on file I/O.